Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Yeah, please do. It really helps us out.
So, imagine you're driving your car across a massive suspension bridge.
Like the Golden Gate or something.
Right, exactly. And you're suspended hundreds of feet in the air above freezing water.
Terrifying, honestly.
Right. You have thousands of tons of steel and concrete stretching for miles, plus these massive gusts of wind pushing against the towers.
Not to mention the combined weight of, thousands of commuting vehicles dynamically shifting all over the deck.
Exactly. So how do the engineers who designed that bridge know with absolute certainty that those steel cables won't just snap?
Or that the deck won't just buckle under all that stress.
Yeah, exactly. So today's deep dive is laser-focused on the hidden mathematical bedrock that answers those exact questions.
It's some really fascinating stuff.
It is. We're looking at excerpts from Chapter 5, Numerical Methods, and our mission today is to understand how engineers figure out the exact stresses, the deformations, and, the absolute limits of incredibly complex physical structures.
Especially when basic textbook mathematical equations just completely and utterly fail.
Right. And it's a profound transition in the history of engineering that we're exploring today.
It really is. I mean, we're looking at a trajectory that takes us from these rigid, incredibly restrictive mathematical grids from decades past.
Right.
All the way to the dynamic, highly adaptable, and almost organic digital modeling systems that hold our modern world together.
It's wild to think about.
Yeah, because this text isn't just about math, It's a story about how human ingenuity found a way to mathematically grasp the messy, highly irregular, and just infinitely complex reality of the physical world.
Okay, let's unpack this. Because to really appreciate where structural engineering is today, we have to start at what I like to call the wall of complexity.
I like that. The wall of complexity.
Thanks. So our source material establishes a baseline by talking about simple geometric structures.
Right, the basics.
Yeah. If you think about the history of engineering, going back to the 1700s and 1800s with mathematicians like Euler and Bernoulli, they developed these brilliant, elegant theories for analyzing structures.
But they were analyzing perfect, simple shapes.
Exactly. A perfectly straight steel beam or a pristine, perfectly round column.
And the text refers to the methods used on these simple shapes as closed-form techniques.
Right. Now, to make sure we're establishing the right foundation for everyone, closed form basically means you have an exact, neat little mathematical equation, right?
That is the essence of a closed-form solution, yeah.
So you plug in your load, you plug in the length of your beam, and the equation just spits out the exact stress.
Right. It provides an exact continuous mathematical function that describes the behavior of the object perfectly at any given point.
So no guesswork.
None at all. If you want to know the bending stress at exactly 3.14159 inches from the end of the beam, the equation gives you the exact, unassailable answer.
It's mathematically pristine.
It is. But the underlying assumption of those closed-form equations is that the geometry is simple and the boundaries are perfectly defined.
Which is never the case in the real world.
Exactly. The mathematics rely on continuity and predictable, uniform shapes.
And that is exactly where the wall of complexity hits.
It's hard.
Yeah, because as the text points out, the moment structures become more complex, which is basically every single thing we build in the modern world, the analyst is forced to completely abandon those exact closed-form equations.
They just don't work anymore.
Right. They have to rely on approximations or physical experimentation or, well, what we're diving into today, numerical methods.
Which is a huge shift in thinking.
It is. So I've been trying to wrap my head around this massive shift from perfect equations to approximations, and I want to try an analogy on you.
Okay, let's hear it.
Think of closed-form techniques, like finding the area of a perfect, clean square on a piece of paper.
Easy enough. Length times width.
Right. It's flawless math.
Yeah.
But let's say you bump your desk and you spill a cup of coffee.
Oh, no.
Yeah. You look down and you want to find the exact, mathematically perfect area of that random, jagged, totally unpredictable splash on the floor.
Simple math completely fails there.
Exactly. There is no length times width for a chaotic coffee splash.
No, there definitely isn't.
So to find the area, you have to break that splash down into 1,000 tiny measurable dots, calculate the area of the dots, and add them up.
I love that. The coffee splash is a brilliant way to visualize the breakdown of closed-form
Oh,
mathematics.
awesome. I'm glad it works.
It really does, because real-world engineering does not happen in perfect spheres or frictionless vacuums.
Right. It's messy.
It happens in the messy reality of the splash. And to understand why we have to break it down into dots, we have to talk about what a physical object actually is in the eyes of a structural engineer.
Okay. What is it?
Well, in the field of solid mechanics, we refer to any continuous solid body as a continuum.
A continuum, meaning something that is continuous without breaks or gaps.
Correct. Whether we're analyzing a solid block of aerospace-grade titanium, a soft rubber tire, or the concrete foundation of a skyscraper, that object is a continuum.
Got it.
And mathematically, a continuum contains an infinite number of points within its volume.
Infinite points.
Yeah.
Right, because no matter how close 2 points are in a solid block of steel, you can always find a point exactly halfway between them.
Exactly. You can zoom in forever.
You can zoom in forever.
And because there are infinite points, if you attempt to write a single perfectly exact closed-form equation to describe how every single infinite point in a highly complex, curved, asymmetrical, grooved object reacts to a combination of heat and pressure,
Let me guess. The math breaks.
the mathematics required to describe that continuous boundary would literally be infinitely long.
Wow.
It is an impossible task for the human mind and an impossible task for any computer.
That's wild.
The governing differential equations of elasticity exist, but they simply cannot be solved exactly for irregular real-world geometries.
Which leaves engineers in a terrifying spot.
It really does.
I mean, you know the laws of physics, you know how steel behaves, but the shape of the engine block you just designed is too complicated to run through the math. You're flying blind.
Well, unless you change the rules of engagement.
Ah, okay.
If you cannot solve the infinite continuum, you must eliminate the infinity.
Eliminate the infinity. I like the sound of that.
This is the entire philosophy behind numerical methods. What numerical methods do is they discretize the continuum.
Discretize.
Yes.
Meaning they turn a continuous object into a discrete, limited set of objects. They chop it up.
They chop it up. They transform a continuous, infinite reality into a finite, manageable collection of mathematical points.
And what do we call those points?
In this field, we call them nodes.
Nodes. Okay.
By discretizing the structure, by dotting your infinite coffee splash, we can take the established laws of elasticity that we know work perfectly on simple shapes and apply them locally to these tiny individual points and the spaces between them.
So you compute what happens at point A.
Right. Then you compute what happens at point B, then point C.
And you calculate how point A pushing on point B affects point C.
Suddenly, you have a mechanism to apply fundamental physics to geometries that would otherwise be mathematically unsolvable.
You bypass the infinite by simply deciding, hey, I'm only going to calculate these 10,000 specific dots, and I'll just assume the material between the dots behaves reasonably.
Exactly. We map out the splash.
But this raises a huge historical question for me.
Sure.
I can understand how a modern supercomputer tracks 10,000 dots. But before we had those computers, how did engineers first attempt to do this?
That's a great question.
Like, how did they try to dot the coffee splash back in the 1920s or 1930s when everything was done by hand with slide rules?
That brings us directly to the earliest attempt to systematize this discretization process.
Okay.
The text highlights this foundational technique as the Finite Difference Method, or FDM.
The pioneer's grid.
It was absolutely a pioneering effort. FDM was one of the earliest mathematical procedures designed specifically for figuring out what happens to stressed, continuous, solid bodies that couldn't be solved with closed-form equations.
So how did it work?
To understand how it works, we have to lightly touch on what it was trying to replace. Differential equations.
Right. And a differential equation is essentially an equation that contains derivatives.
Exactly.
And a derivative, at its core, is a measure of how a function changes as its input changes. It's looking for a rate of change at one exact, infinitesimally small point.
Spot on.
Like a speedometer telling you your exact speed at a frozen millisecond in time, rather than your average speed over a whole road trip.
That is a highly accurate way to frame it. The governing equations of solid mechanics are differential equations. They are obsessed with finding the instantaneous rate of change of stress or displacement at an infinitesimally small point.
But as we established, finding that exact instantaneous change across a wildly complex geometry is impossible.
Exactly. So the finite difference method fundamentally works by abandoning the exact derivatives.
Abandoning it completely.
Yes, it replaces those complex derivatives with something called difference quotients.
Difference quotients.
Yes. And it calculates these quotients at discrete, highly specific mesh points across the domain of the object.
Okay, let me see if I can translate the mechanics of a difference quotient, because I want to make sure the underlying logic is really clear here.
Go for it.
If a true derivative is trying to measure an instantaneous rate of change at one microscopic point, FDM essentially says that is way too difficult.
Way too hard for a human.
Right. So let's just put a grid over the object. We'll look at a point on the grid,
Oh.
and we'll look at the point right next to it. We will see the finite difference in value between those 2 points divided by the distance between them, and we will just use that as our rate of change.
Yes.
It's an approximation of the slope.
That is precisely the mechanism.
Right.
You are taking the true continuous curve of reality, and you are approximating its slope by drawing a straight line between 2 discrete points on a grid.
You're looking at the finite difference.
Exactly. It is a brilliant mathematical workaround, deeply rooted in something called a Taylor series expansion.
Oh man, calculus flashback.
I know, right? But basically, it allows you to approximate the value of a function at one point based on the function's value and derivatives at a neighboring point.
Okay, that makes sense.
By replacing all the terrifying derivatives in the governing equations with these manageable difference quotients, engineers could suddenly set up a system of algebraic equations.
Oh, and algebraic equations, unlike differential equations, can actually be solved by hand.
If you have enough time and enough patience, yes.
What's fascinating here is how this incredible mathematical workaround was simultaneously its own worst enemy.
It really was.
Yeah, the text points out that FDM was fundamentally constrained by the very grid it relied upon to work.
The disadvantages are laid out very clearly in the source material.
Right. FDM relies on calculating these variables at rigid mesh points that operate in a strict uniform grid.
It usually requires perfect rectangles.
Which means it requires immense geometric order. You need perfectly spaced horizontal rows and vertical columns to make those difference interval. Quotient calculations actually line up with each other mathematically.
The math of FDM is incredibly fragile in that regard.
Really? Fragile how?
Well, a difference quotient relies on a known uniform step size. The distance between point A and point B needs to be the same as the distance between point B and point C.
Oh, I see.
If the grid spacing becomes irregular, the approximations of the derivatives lose their accuracy very quickly.
Which leads to a massive real-world problem. Because if I'm an engineer trying to model the sweeping, elegant, continuous curve of an airplane wing, a shape defined by aerodynamics, and I'm using the finite difference method, I am forced to map that beautiful curve using a mathematical grid made of perfect, rigid rectangles.
It's a nightmare for aerodynamics.
It sounds exactly like trying to build a smooth, highly curved aerodynamic sports car out of large, blocky Minecraft cubes.
That is a great visual.
Right. Because no matter how you arrange the cubes, no matter how small you make them, the outer edges of that car are always going to be jagged.
It will step up, step over, step up, step over.
Yeah, it's never going to be an actual continuous curve.
The Minecraft analogy perfectly captures the fatal flaw of FDM when applied to complex engineering.
So the text calls this out specifically.
Yes.
Right.
In fact, the text explicitly lists this as a primary failure. It notes the severe difficulties of FDM when it comes to imposing boundary conditions on curved boundaries.
And it also mentions the absolute inability to utilize non-uniform or non-rectangular meshes. So explain the boundary condition failure for me.
Sure.
Because why does the jagged Minecraft edge ruin the math? I mean, if the overall shape is roughly right, shouldn't the stresses be roughly right?
You would hope so, but structural mechanics is incredibly sensitive to geometry, particularly at the boundaries.
Okay, so define a boundary condition for us.
A boundary condition is essentially how the object interacts with the outside world.
Give me an example.
If a steel plate is bolted to a wall, the bolted edge is a boundary condition where displacement is 0. It can't move.
Okay.
If wind is blowing against an airplane wing, the surface of the wing is a boundary condition experiencing a distributed pressure load.
Right, the outside edge where the action happens.
Now, apply your Minecraft analogy to the math.
Okay.
If your real-world object has a sweeping curve, but your mathematical model is built out of rigid rectangular blocks, those blocks will stick out where the curve should dip in.
Right, you get those artificial stairs.
They will create artificial jagged right angles along the boundary.
Then why is that bad?
Because in real life, wind flows smoothly over a curve, distributing pressure evenly. In the FDM mathematical model, that pressure hits the sharp corner of a rectangular grid point.
Oh, I see where this is going.
In the physical world, sharp interior corners create massive stress concentrations, places where forces amplify dangerously.
So because your mathematical grid has artificial corners,
Yeah.
your equations will calculate stress concentrations that do not actually exist in reality.
Exactly. The math will tell you the wing is failing simply because of the jagged corners of your grid.
That is wild.
That's a huge problem.
The tool you are using to check for failure actually hallucinates failure because of its own shape.
It is a severe limitation.
So how do they fix it?
To fix it in FDM, you either have to use highly complex, mathematically torturous interpolation schemes at the boundary, which defeats the purpose of the method's simplicity.
Right, too much math.
Or you have to make the grid so incredibly dense that the steps become microscopic.
Just use smaller Minecraft blocks.
Exactly. But making the grid denser means adding thousands more points, which means thousands more equations.
And in an era before digital supercomputers, that was entirely unfeasible.
Completely impossible for humans to calculate.
So FDM was a critical first step. It proved that discretizing a continuum was possible.
Yes, it did.
But the moment the engineering problems got curvy, or organically shaped, or geometrically irregular, the method just hit a brick wall.
Engineers were essentially trying to force a rectangular peg into a beautifully curved hole, and the math was breaking.
This profound limitation, this inability to accurately map curved boundaries with rectangular grids, that must have been a massive bottleneck in structural engineering throughout the early 20th century.
It forced engineers and mathematicians to desperately search for a more flexible, adaptive mathematical framework.
They needed a way to break up the object that didn't rely on rigid, perfectly spaced rows and columns.
They needed a mesh that could mold to reality, rather than forcing reality to mold to a mesh.
And that desperate search is what gave birth to what we now know as the Finite Element Method. FEM. This is the absolute heavyweight champion of modern engineering.
Without a doubt.
Every piece of software, every CAD program, every safety test uses some form of FEM today.
It is ubiquitous.
And our source material provides a really fascinating historical breakdown of how FEM actually evolved. I think it's crucial to trace this evolution because FEM wasn't just invented on a Tuesday by one person.
No, not at all.
The text states it evolved from a mix of things. It took the discretization concept from the Finite Difference Method. It incorporated trial functions from variational methods and weighted residuals, and it leaned heavily on structural analogs.
It was a true decades-long synthesis of different mathematical philosophies.
So how is it different from FDM?
To understand the leap, we have to look at how FEM fundamentally differs from FDM. FDM was obsessed with differential equations. It tried to approximate the derivative at specific points.
Right, the difference is quotients.
FEM took a completely different path. FEM utilizes an integral formulation.
An integral formulation, okay.
Instead of looking for a derivative at a single point, FEM takes the geometrically complex domain, the whole physical object, and breaks it down into a finite collection of simpler subdomains, which we call finite elements.
The elements, the actual building blocks.
Yes. And instead of trying to satisfy a differential equation at a specific point, FEM attempts to minimize the overall error across the entire volume of that element.
Okay, so it looks at the whole block, not just a point.
This is where the variational methods come in. Within each element, the unknown variable, let's say how much the metal displaces when you push on it, is approximated by continuous, piecewise smooth functions.
Okay, we need to break down continuous, piecewise smooth functions.
I know, it's a mouthful.
If I'm an engineer trying to model a solid object under load, what does that actually mean?
Think of it this way. In FDM, you only knew the answer exactly at the rigid grid points. You had no idea what was happening in the blank space between point A and point B.
Right, it was just empty space mathematically.
FEM solves this. When you create a finite element, you assume a mathematical function that describes the behavior across the entire element.
The whole thing.
It's often a polynomial equation. So if you know how much the corners of the element move, the piecewise function allows you to calculate the exact displacement of any location within that element.
Oh, wow.
It's a continuous function, but only for that specific piece of the whole structure.
Ah, so it's like a patchwork quilt.
A patchwork quilt is an excellent visualization.
Each patch has its own continuous equation, but they are all stitched together at the seams to cover the whole bed.
Exactly. And tracing the historical timeline the text gives us really highlights how long it took to figure out how to stitch those patches together.
It starts back in the 1940s, right?
It does. We have engineers like Krennikov, McHenry, and Newmark The text notes they used a lattice of line elements for solving stresses in continuous solids.
A lattice of line elements. This is the structural analog part of the evolution, right?
Yes, it is.
They were literally imagining a solid block of concrete or a solid steel plate as being made up of a complex three-dimensional web of tiny microscopic rods and beams.
It's like they were imagining a solid continuum as a microscopic jungle gym.
It was a brilliant conceptual leap, driven entirely by necessity.
Engineers already had highly developed, highly accurate methods for solving complex trusses. Structures made of individual beams connected at joints like an old railroad bridge.
The math for a truss was well understood.
So Renikoff and others essentially said, what if we pretend this solid steel plate isn't a solid continuum, but is actually just a really dense truss?
That's so clever.
They modeled a 2D plane of solid material as an equivalent framework of elastic rods. It was a structural analog using a known structural framework to approximate an unknown continuum.
It's an incredible hack. You take the math, and you apply it to the problem you don't. But while a lattice of rods is great, a rod is still just a straight line. The true paradigm shift, the moment that set the stage for modern FEM as a true surface and volume modeler, happened in 1943.
Yes. 1943 is a landmark year in this field. A mathematician named Richard Current published a paper where he suggested using piecewise polynomial interpolation over triangular subregions to model torsional problems.
Triangles.
Triangles.
It seems almost absurdly simple. We go from rigid FDM rectangles to a jungle gem of rods to a mathematician just suggesting triangles.
It sounds deceptively simple, but Current's introduction of the triangular subregion was the ultimate geometric game changer for modeling non-rectangular shapes.
Why is a triangle so much better than a rectangle?
Think back to the problem that plagued the finite difference method. Think back to your Minecraft card.
Okay, the jagged edges.
If you are mathematically restricted to using squares and rectangles, you can never, ever build a smooth, sweeping curve. Your boundaries will always be jagged. But if you can use a triangle...
You can angle them. You can tilt a triangle. You can stitch a bunch of differently sized triangles together to follow a contour.
Exactly.
A tight cluster of small triangles can approximate the smooth edge of a circular hole or the sweeping curve of an aerodynamic wing infinitely better than a rigid grid of squares ever could.
Currents essentially solves the FDM boundary problem by changing the shape of the grid itself.
He freed the mesh from the tyranny of the rectangle.
That's a great way to put it. The triangle provided the geometric flexibility that FDM completely lacked. You could now map complex, highly irregular boundaries simply by adjusting the size, the aspect ratio, and the orientation of the triangles.
So you use big ones where it's flat and small ones where it curves.
You could use large triangles in the middle of a plate where nothing interesting was happening and tiny, dense triangles near a curved edge to capture the detail. It was revolutionary. But, as with all theoretical breakthroughs in the 1940s, there was a massive practical catch: the math. Current published this brilliant theory in 1943. But the calculations required to solve these highly interconnected triangular networks using variational methods were agonizingly complex.
I can only imagine.
To solve the system, you have to create a massive set of simultaneous algebraic equations. Doing this by hand for a model with 50 triangles could take weeks.
And for a complex 3D shape.
Humanly impossible.
Which brings us to the 1950s and the technological rescue of FEM.
The computers arrive.
The text mentions that the advent of digital computers made it practical for engineers to actually formulate and solve stiffness equations in matrix form.
This led to a classic foundational paper in 1956 by Turner, Clough, Martin, and Top, which successfully applied these methods to complex aerospace structures.
And then in 1960, Clough officially coined the term finite element.
It all came together.
So I have to ask, looking at this timeline, it really sounds like all this incredible groundbreaking math in the 1940s was just theoretical torture for the humans trying to calculate it.
It was definitely a grueling process.
Did the invention of digital computers basically rescue FEM from being just a really cool but totally unusable idea locked in a mathematician's notebook?
Without a doubt. The finite element method and the digital computer are entirely symbiotic. Digital computers were the oxygen that FEM needed to breathe.
Because they could do the math.
To truly understand why, you have to understand what a matrix stiffness equation actually is and why a human brain hates it.
Okay, break down the matrix for us.
Let's go back to the basic physics of a spring. The most fundamental equation in elasticity is Hooke's law. Force equals stiffness multiplied by displacement.
F equals kx.
Exactly. If you pull a spring with a certain force, it stretches a certain distance based on how stiff the spring is. In FEM, when you break a solid object into hundreds of finite elements, you're essentially treating the object as an incredibly complex network of hundreds of highly specialized springs.
Every element has its own stiffness.
Right, because a piece of steel resists pulling, just like a spring does.
Okay, that makes sense.
But here's the problem. These elements are not isolated, they are connected.
They share borders.
If you push on element number 1, it displaces. But because it's physically connected to element number 2, it pushes on element 2.
Which pushes on element 3 and element 4.
The force propagates through the entire network. A matrix is essentially a massive, highly organized mathematical spreadsheet that tracks every single one of those interconnected relationships simultaneously.
So it's not just one equation, it's thousands of equations that all rely on each other.
They must be solved simultaneously. If you have a model with 1,000 connection points, you have thousands of equations.
Ouch.
Solving a system of just 20 simultaneous linear equations by hand using matrix algebra is highly prone to human error. A single dropped negative sign ruins the entire model.
And what about 10,000 equations?
Solving a matrix with 10,000 equations by hand is impossible. But a computer eats massive matrices for breakfast.
It's just simple arithmetic scaled up to infinity.
Exactly. It is incredibly easy and blisteringly fast for a computer to execute the Gaussian elimination required to solve thousands of simultaneous linear equations.
So the computers didn't just help.
So the computer revolution of the 1950s didn't just help FEM, it sparked the modern era of automatic adaptive structural analysis.
It changed everything.
As the text notes, this computational power paved the way for automated mesh generation, where the computer algorithms actually build the millions of triangles for you.
Oh, you don't draw them by hand anymore.
Thankfully, no. And it allowed for advanced computer graphics and pre-processing, which is how we build the CAD model, and post-processing, which is how we visualize the results with those colorful stress maps we are all so used to seeing today.
Red means danger, blue means safe.
Exactly.
So we have the history mapped out, we have our triangles replacing our rigid rectangles, and we have our digital computers humming away in the background, crunching the matrices.
Now we need to look under the hood.
We do. We need to look at the actual anatomy of a modern finite element model, exactly as it's described in Chapter 5.
Let's do it.
The text establishes that FEM discretizes a continuous elastic structure into elements. And the behavior of each individual element relies on a few key things.
But what?
It relies on material properties. Is it made of high-carbon steel, or is it made of soft rubber? It relies on geometric properties. How thick is it?
Makes sense.
It relies on the loads applied to it. Is it a static weight, a dynamic vibration, or a thermal load from extreme heat? But crucially, the text says the behavior relies on the loads and displacements at the nodes.
Yes. If you want to understand the true anatomy of FEM, you must focus on the nodes.
Yeah.
The elements are the volumetric spaces filling the shape, but the nodes are the mathematical anchors.
Here's where it gets really interesting, and I want to propose another analogy to ground this.
Bring it on.
Imagine the structure you are testing. Say a brick wall is actually a giant Lego castle.
Okay, a Lego castle.
The physical plastic Lego blocks themselves. Those are the elements. The plastic blocks hold the physical properties. They have mass. They take up physical space. They represent the stiffness of the material.
Okay, I'm with you.
But the little cylindrical bumps on the top of the block and the little tubes on the bottom that physically snap the blocks together, those connection points are the nodes.
That analogy perfectly captures the mechanics of the system. The text specifically states that the element's nodes are the fundamental governing entities of the element.
Why are they the governing entities?
Because in a finite element model, the plastic blocks the elements do not technically touch each other along their flat faces. Mathematically, they only interact at the bumps. They only interact at the nodes.
Wait, really? The faces of the elements don't pass force to each other?
In the foundational mathematical formulation, no. The forces are transmitted entirely through the nodal connections.
That's crazy.
The node is where element A mathematically shakes hands with element B. Furthermore, the nodes are where you assign your boundary conditions.
Going back to the gluing to the table.
Exactly. If your Lego castle is glued to a table, you don't glue the plastic face. Mathematically, you take the nodes at the very bottom.
Okay, that makes perfect sense.
And finally, the nodes are where external forces are applied. When you press down on the top of a Lego castle with your hand, the mathematical model applies that force vector directly to the nodes on the top surface.
Which pushes the nodes down.
Those nodes displace, which strains the element, which transmits force to the nodes below it, cascading through the entire object. The nodes dictate exactly how the force passes through the continuum.
And the text brings up a critical term regarding these nodes, which is central to how they move. It says a node can possess up to 6 degrees of freedom, or doof.
Yes, degrees of freedom.
It specifies 3 translational degrees of freedom and 3 rotational degrees of freedom.
The degrees of freedom are how we define the capacity for movement in three-dimensional space. Every node in a 3D model exists at a specific coordinate, x, y, and z.
Like a graph.
The 3 translational degrees of freedom represent the node's ability to move linearly along those axes. It can translate up and down the y-axis, left and right along the x-axis, or forward and backward along the z-axis.
So that's translation, just sliding around. What about rotation?
The 3 rotational degrees of freedom represent the node's ability to twist or pivot around those same 3 axes. If you think of an airplane, this is pitch, yaw, and roll. So a single node in a 3D space has 6 distinct ways it can react when a force hits it. It can move in 3 directions, and it can twist in 3 directions.
6 degrees of freedom per node. So if I have a complex model with 1 million nodes, the computer is tracking 6 million independent variables of movement.
Precisely. And this is where that massive mathematical spreadsheet, the matrix, comes into play.
Right.
In a FEM model, every single element has a local stiffness matrix that defines how its specific nodes will move relative to each other based on its shape and material.
But they don't act alone.
But a single element doesn't exist in isolation. So the computer software takes all of those tiny local matrices and it aggregated them.
That adds them all up.
It globally assembles them through the common nodes they share into one massive, overarching global system matrix.
It snaps all the Legos together into one unified mathematical fortress.
It does. And once that massive global system matrix is assembled and the external loads and boundary conditions are applied, the computer algorithm solves the system.
It runs the numbers.
It solves for the unknown displacements. It calculates exactly how much every single node in the entire model translates or rotates under that specific stress.
So it tells you exactly where they all moved.
It determines that node number 45,912 moved 0.02 millimeters in the x direction and rotated 0.1 degrees around the z-axis.
Okay, so we've solved for the nodes. We know how all the connection bumps on the Legos moved.
We do.
But knowing how a bump moved doesn't tell me if the plastic block is going to shatter. How do we get from nodal displacement to actual material stress?
That is the final crucial step of the FEM process. Once you know exactly how the nodes have displaced, you can determine what happened to the element between the nodes.
The actual plastic part.
If node A moved to the left and node B moved to the right, the element between them has stretched.
That makes sense.
We use the continuous piecewise smooth functions we talked about earlier, the interpolation functions, to calculate the strain field across the element based on the nodal displacements.
Strain being the physical deformation, the stretching or compressing of the material.
Correct. And once you have the strain, you use what the text calls the constitutive equations of elasticity.
Okay, constitutive equations.
These are equations derived from the material's properties like Young's modulus and Poisson's ratio. They relate strain directly to stress.
So you plug the stretch into the equation and it spits out the stress.
So the displacement of the nodes gives you the strain of the element, and the material properties convert that strain into a stress value.
Got it.
And that stress value is what tells the engineer whether the steel will yield or whether the concrete will crack.
It is an incredibly elegant chain of logic. You figure out how the connecting bumps move. That tells you how the plastic block is deforming. And the material science tells you if that deformation is lethal.
It's a beautiful system.
But looking at Table 5.1 in the text, it becomes very clear that the Lego analogy only goes so far, because not all of these mathematical blocks are the same size or shape.
No, they are not.
The text outlines an entire element library that commercial FEM software uses. We aren't just limited to one type of 3D block.
The element library is the core of an engineer's toolkit. Finite element analysis is not a one-size-fits-all process.
What dictates which one you use?
The geometry and the physics of the problem dictate what kind of math you should use. The text breaks this library down into distinct dimensional categories.
Like 1D, 2D, 3D.
First, you have 1D line elements. These are simple elements with just 2 nodes, one at each end.
Like a mathematical stick.
Exactly. And even within line elements, you have variations. The text lists the truss element.
A truss.
A truss is a pin-ended bar that mathematically can only take tension or compression. It only pulls or pushes along its exact axis. It cannot bend.
So if you push it from the side, mathematically it has no resistance.
It would offer zero stiffness to a lateral load. If you need a line element that resists bending, the library offers a beam element. A beam element includes rotational degrees of freedom at the nodes, allowing it to calculate bending moments and shear forces.
And what if it needs to do everything?
And if you need an element that can handle axial loads, bending and twisting all at once, you use a frame element.
So you use line elements for long, thin structural members. Then the library steps up a dimension to 2D surface elements.
Yes.
These are used for planes or thin shells. The text lists 4-node and 8-node quadrilaterals, so 4-sided shapes like squares or rectangles, and 3-node and 6-node triangular elements.
Surface elements are vital for modeling structures where one dimension is significantly smaller than the other two.
Like what?
Think of a thin, flat steel plate or the skin of an airplane fuselage, or an axisymmetric structure like a cylindrical pressure vessel.
Okay, things that are basically flat.
Instead of modeling the entire thickness of the plate with 3D blocks, you model the midplane of the plate with a 2D surface element, and you simply tell the computer, hey, mathematically treat the zero-thickness triangle as if it is a 1/4 inch thick.
Oh, that's a clever shortcut.
It is a massive computational shortcut.
And then we finally step into the full third dimension with solid elements, the true volumetric blocks.
Yes, the 3D ones.
The text lists the 8-node hexagonal element, the classic 6-faced brick shape. We have the 6-node pentagonal element, which is a wedge, and we have the 4-node tetrahedron, affectionately known in the industry as the tet.
Solid elements are necessary when the stress state is truly three-dimensional. When a structure is thick and complex, like a cast iron engine block or a solid steel anchor, the stress doesn't just flow along a surface, it flows through the volume.
Right.
A surface element cannot capture through thickness stress gradients. You need a 3D brick or a tet to capture how the forces dive into the core of the object.
And finally, the text lists some weird ones, what it calls special purpose elements. It lists gap elements, hook elements, and rigid constraints.
These are fascinating because they handle what we call nonlinear contact problems.
Nonlinear contact.
Think about a gap element. Most structural elements are securely attached to each other. But what if two pieces of steel are just resting near each other with a 1 millimeter gap between them?
Oh, so they aren't touching yet.
If they are pulled apart, they don't interact. But if they are pushed together, they will travel 1 millimeter, physically collide, and suddenly start transferring massive amounts of force.
And a regular math spring can't do that.
A standard spring element can't model that sudden collision. A gap element mathematically represents a space that offers zero resistance until it closes, at which point it offers infinite resistance.
The methodology behind choosing from this massive library seems crucial. An engineer doesn't just import a CAD file, hit an auto mesh button, and let the software randomly guess what to use.
You'd hope not, no.
They have to deeply understand the physics of what they are testing to build the mesh correctly.
The mesh generation is where engineering judgment is paramount. If you are analyzing a simple pin-ended suspension rod, you use a line element.
Why is that?
Because physically, it behaves exactly like a truss in tension. And computationally, calculating a simple 2-node line element takes milliseconds.
Right.
If you used a million 3D solid brick elements to model a simple tension rod, you would get the exact same answer, but it would take the computer an hour to solve it. It's a waste of resources.
Now, I want to bring up something you touched on when listing the surface elements. You mentioned a 4-node quadrilateral, which makes sense, 4 corners on a square.
Yeah.
But you also mentioned an 8-node quadrilateral.
I did, yes.
A square only has 4 corners. Where do the other 4 nodes go? The text refers to these as mid-side nodes.
This is a brilliant mathematical advancement. A standard 4-node quad has a node at each of its 4 corners. The mathematical interpolation function that connects those corner nodes is linear.
It's a straight line.
It assumes the edge of the element is a perfectly straight line, and it assumes the displacement changes linearly from one corner to the next.
Which is fine if you are modeling a flat, boring plate.
Exactly, but what if you are modeling a curved bracket? An 8-node quad takes the 4 corner nodes, and it adds an additional node precisely in the middle of each of the 4 edges.
The mid-side node.
These are the mid-side nodes. By adding a third point along an edge, the mathematical interpolation function upgrades from linear to quadratic.
Oh, because you need 3 points to define a curve. 2 points just make a straight line.
Precisely. Having a node in the middle of an edge allows that mathematical boundary to physically curve into a parabola within the software, rather than being forced to remain a rigid straight line.
So it actually hugs the curve.
It vastly increases the accuracy of the element when modeling curved geometries. Instead of a jagged Minecraft edge, the element physically bends to match the CAD geometry.
That's so smart.
Furthermore, quadratic elements can capture highly complex, nonlinear stress gradients inside the element much more accurately than linear elements.
Okay, so that raises a very practical question to try and tie this massive library together. Let's go back to the scenario from the top of the show.
The suspension bridge.
Right. I am an engineer, and I am tasked with modeling a massive, incredibly complex suspension bridge like the Golden Gate Bridge. I have thousands of feet of roadway deck. I have massive solid concrete towers. I have hundreds of braided steel suspender cables and huge main cables.
It's a huge project.
If I'm using FEM, I can't just make the entire bridge out of tiny 8-node solid 3D bricks, right?
Yeah.
I mean, to capture the detail of a cable and the mass of a tower, there would be billions of nodes. Wouldn't that completely crash my supercomputer or take 6 months to solve?
You've hit on the exact art of finite element analysis. It is not just about raw mathematical power, it is an art form of computational efficiency.
Because you can't just brute force it.
If you modeled an entire suspension bridge with millions of highly detailed 3D solid brick elements, yes, the computational expense would be astronomical. The system matrix would be unsolvable in any reasonable time frame.
And worse.
And worse, it would be entirely unnecessary. This is exactly why the element library exists. A skilled analyst acts like an orchestrator, combining different dimensional elements to achieve maximum accuracy with minimum computational cost.
Walk me through the orchestration of the bridge.
Let's start with the massive main cables and the vertical suspender ropes dropping down to the deck.
Okay.
Cables, physically, are incredibly long and thin, and they only possess tensile stiffness. They cannot resist bending. If you push a cable sideways, it just flops over.
Right.
Therefore, you do not need 3D bricks to model them. You model those massive cables using 1D line elements, specifically truss elements, because they only take tension.
So a 1,000-foot, multi-ton steel-braided cable is represented mathematically in the model by a single, perfectly straight line with just 2 nodes.
Exactly. You assign that single line, the cross-sectional area, and the material stiffness of the real cable. And mathematically, it behaves identically to the real thing, but it only requires 2 nodes to solve instead of 2,000.
Wow, so you just saved massive amounts of computing power.
Massive amounts. Next, look at the roadway deck. It is very long and very wide, but relatively thin compared to its span. It behaves physically like a plate in bending.
So what do you use for that?
So you model the entire roadway deck using 2D surface elements like 4-node quadrilaterals.
So the deck is basically represented as a flat sheet of paper, but the math treats it like thick steel.
Correct. You define the thickness in the element properties, bypassing the need for volumetric meshing.
So where do the 3D bricks come in?
Now, where do you use the 3D solid elements? You use them only where the geometry and the stress states are truly complex and three-dimensional.
Like the foundations?
You would use 8-node brick elements to model the massive concrete anchorage blocks buried in the ground where the main cables splay out and bolt into the foundation. You need to know exactly how that localized 3D stress flows through the concrete to ensure it doesn't crack under the tension.
And what about the special purpose elements?
You would utilize gap elements where the roadway deck meets the expansion joints at the towers. A bridge deck physically expands in the summer heat.
Right, thermal expansion.
A gap element allows the roadway mesh to freely translate in the model until it travels a prescribed distance the size of the physical gap, at which point the gap element closes and transfers the compressive force into the tower, exactly mimicking reality.
I am marveling at the precision of that. You orchestrate all these different mathematical instruments, the 1D lines, the 2D sheets, the 3D blocks, to play together perfectly to create a single, efficient, solvable model.
It's beautiful when it works well.
But our source material takes a very sharp pivot right after explaining this brilliance. It notes that despite this massive, highly curated library of elements, despite the supercomputers and the mid-side nodes, FEM is, at its absolute core, fundamentally an approximation.
It is.
We are still just dotting the coffee splash. We haven't solved the infinity problem. We just bypassed it. And approximations, by their very nature, breed dangerous errors.
They do. And the text does not shy away from this reality. In fact, it states plainly as a warning to analysts, Errors are inevitable.
Inevitable. That's a strong word.
Any mathematical model that replaces a continuous physical reality with a finite discretized approximation is going to generate errors. The text breaks these inevitable errors down into two main categories that every engineer must understand.
Okay, let's go through them.
First, you have computational errors. These are the round-off errors stemming directly from the computer's floating point calculations.
Floating point calculations. This is basically when a computer tries to calculate an irrational number, or a number with an infinite decimal, and it has to just chop the decimal off somewhere, right? Maybe at the 8th or 16th decimal place.
Precisely. A computer has finite memory. It cannot store an infinitely long number, so it rounds it off.
But if I'm designing a bridge, who on earth cares about the 16th decimal place of a stress calculation? That's smaller than an atom. Why is that an error worth noting?
In isolation, it isn't. If you round off one number at the 16th decimal place, it has zero impact on reality. But remember the matrix. Remember the thousands of simultaneous equations.
Oh, right.
In a complex FEM model, the computer isn't doing one calculation. It is multiplying and dividing numbers millions of times across a massive system.
And the errors compound.
If node 1 has a microscopic round-off error, and that error is multiplied into the equation for node 2, which is multiplied into node 3, that tiny microscopic truncation can propagate and snowball through the Gaussian elimination process into a massive, structurally significant miscalculation.
It can pollute the entire matrix.
It's the butterfly effect inside a spreadsheet.
Exactly. That's terrifying.
However, the text reassures us that most modern commercial finite element codes the software is used by major industries have highly robust mathematical algorithms specifically designed to minimize and handle these round-off errors.
Oh, okay.
They use double precision floating point arithmetic, so the analyst, the human engineer running the software, generally doesn't have to lose sleep over the computer's raw arithmetic. The computer manages its own rounding.
So what does the human have to lose sleep over?
What they must obsess over, what they are entirely responsible for, are the discretization errors.
Discretization errors.
Yeah.
This is where the human messes up the Lego build.
This is where the geometric approximation fails.
Yep.
Discretization errors occur because the true physical structure, the continuum, varies continuously in its shape and its stress.
Right.
But you are using a finite number of predetermined geometric shapes and polynomial functions to model it. There is an inherent mismatch between the true physics and the mathematical representation. You are forcing a smooth reality into a rigid box.
And the text gives a phenomenal, very specific case study of a discretization error that can completely blindside an engineer. It's the hole in the plate scenario.
A classic problem.
Let's walk through this carefully. The text asks us to consider a thin, flat, rectangular steel plate, and it has a perfectly circular hole punched right through the dead center of it.
Okay.
The text shows what happens when an engineer tries to model this plate, and specifically the area around the hole, using three-node, plane-stress triangular elements. Basically, simple, flat, linear triangles.
The basic triangle.
And the text explicitly points out two fatal flaws of using the three-node triangle in this specific scenario.
The first flaw is purely geometric. We discussed this earlier with currents triangles. A standard three-node triangle has three nodes, one at each corner, connected by three perfectly straight sides.
Right, they can't curve.
The text points out that because of the linear interpolation function, these sides must mathematically remain straight, even after deformation. So if you attempt to model the sweeping, perfectly circular edge of the hole using a handful of straight-edge triangles, you completely fail to map the geometry.
It's the Minecraft problem all over again.
You get a jagged geometric octagon or dodecagon instead of a smooth circle. You have introduced an artificial geometric boundary error right where the stress is going to be highest.
It's bad.
But the second problem, the mathematical problem, is much, much worse.
The text says the fundamental flaw is that the simple three-node triangle assumes constant strain throughout the entire element. This is known as a constant strain triangle, or a CST.
This is the true trap for the unwary analyst. We need to define what constant strain actually means in this context.
Okay, please do.
Because the triangle only has nodes at the corners, and because it uses a first-order linear polynomial to guess what happens between the corners, mathematically, the element is only capable of calculating a single uniform value for strain across its entire surface area.
So no matter how big the triangle is, it can only output one number for the whole shape.
Exactly. It can only provide an average strain value, which is effectively located at the dead center, the centroid of the triangle. The entire element glows with one uniform color on the stress map.
So what's wrong with an average?
Now, consider the physical reality of a hole in a plate. When you take a solid plate and you pull on the ends, the stress flows through the metal evenly, but when it hits the hole, the stress lines have to detour around the empty space. They bunch up.
Like traffic on a highway.
Exactly. This creates what we call a stress concentration.
So the stress right next to the edge of the hole is way higher than the stress an inch away from the hole.
Massively higher. For a perfectly circular hole in a wide plate, theoretical elasticity dictates that the stress exactly at the edge of the hole is exactly 3 times higher than the average stress of the plate.
3 times higher.
It is a massive, incredibly localized spike. The strain changes incredibly rapidly over a distance of a few millimeters as you move away from the edge.
And here is where the 3-node triangle completely betrays the engineer.
Yes. The large 3-node triangle cannot mathematically see that rapid, localized change. It spans across the high stress at the edge of the hole and the lower stress further away.
Oh, I see.
Because it is a constant strain element, it simply looks at the high number and the low number, and it averages them out into one single, mediocre, safe-looking number. It completely smears out the stress peak.
So what does this all mean in practice? I want to push back on this geometry for a second because if I'm thinking about the real-world implications, this sounds genuinely terrifying.
It is.
Let's step away from a theoretical plate and look at reality. Let's say I'm an aerospace engineer. I'm running finite element analysis on a new aluminum airplane fuselage. And that fuselage has a window in it.
A window is just a hole in a plate.
Right. And let's say I'm lazy or I don't understand discretization errors, and I use these basic 3-node constant strain triangles around the window, because they only give me an average constant strain across their surface. Couldn't that cause my multi-million-dollar model to completely miss a massive, sharp spike in stress right at the exact corner of the window's edge?
It absolutely could.
The computer model would output a nice, safe, average blue color. It would say the stress is well below the yield strength of the aluminum. But in real life, because the stress concentration is masked by the math, the metal could be actively ripping apart at the microscopic level.
You're exactly right.
The plane could fail in real life, even if the supercomputer explicitly says it's perfectly fine.
This raises an important question, doesn't it? It's the fundamental question of numerical modeling. Are you modeling reality, or are you just playing a video game with math? It is about the danger of blindly trusting our tools without deeply understanding the underlying mathematics that govern them. Your airplane window scenario is not an exaggeration. It is exactly what can happen if an analyst is ignorant of discretization errors and element formulation.
So the computer isn't wrong, the engineer is.
The computer isn't lying to you. It is doing exactly what you told it to do. You told it to use an element that averages strain, so it dutifully averaged the strain right over the most critical, life-threatening stress spike in the entire structure.
And the results?
The results predicted using that model will be, as the text mildly puts it, relatively poor. In reality, they are potentially catastrophically poor.
So how do we fix it? How do we stop the plane from falling out of the sky in our simulation? The text must offer a way out of the constant strain trap.
The text gives 2 direct, actionable solutions to solve the hole in the plate problem. The first solution is the brute force method. Simply increase the mesh density.
But triangles.
If the error comes from a large triangle averaging a large area, the solution is to use way more, much smaller elements. Instead of placing 10 big triangles around the hole, you pack the boundary with 1,000 microscopic triangles.
Because if a constant strain triangle is microscopically small, its average is basically measuring a single tiny point anyway.
Exactly.
As the triangles get smaller, their localized average gets closer and closer to the actual true peak spike in stress.
You converge on the true mathematical answer by overwhelming the problem with nodal density.
But doing that, adding thousands of new triangles adds thousands of new nodes, which adds thousands of new degrees of freedom, which massively drives up our computer processing time and matrix size. We're back to bogging down the computer.
Which is why the brute force method is often inefficient. The elegant fix, the vastly better alternative the text strongly suggests, is to use a better mathematical tool. Swap out the 3-node linear triangle for the 8-noded quadrilateral element we discussed earlier.
The one with the mid-side nodes.
Yes. Because the 8-node quad utilizes mid-side nodes, it employs higher-order quadratic interpolation functions.
Meaning the math inside the element is fundamentally smarter than the 3-node triangle.
Vastly smarter. The higher-order function solves both flaws simultaneously. First, geometrically, it allows the edges of the element to mathematically curve, beautifully and accurately mapping the actual circular boundary of the whole without the jagged Minecraft steps.
Which solves the geometry problem.
Second, and much more importantly, the quadratic function is not restricted to constant strain. It allows the strain to vary non-linearly within the element itself.
Oh, so it doesn't average the whole block.
It does not average. A single 8-node quadrilateral element can calculate that one edge of the element, the edge touching the hole, is experiencing massive yielding strain, while the opposite edge of the exact same element is experiencing almost zero strain.
It can see the spike.
It captures the rapid gradient. It maps the change. By using higher-order elements, you capture the peak stress concentration accurately with far fewer elements, saving computing power and, more importantly, saving the engineer from that catastrophic discretization error.
Okay, so we've firmly established that FEM is an incredibly powerful world-building tool, but you have to be wildly, painstakingly careful about how you build your mesh.
You absolutely do.
You have to choose the right elements, you have to watch out for constant strain, and you have to pack your interior volumes with 3D bricks or TETs to figure out how the stress flows inside a solid object.
That's the summary.
Which makes me wonder, if filling a massive 3D solid object like a thick metal casting with millions of tiny solid brick elements causes all these interior discretization headaches and requires massive supercomputing power to check all those internal hidden nodes, is there a way to bypass the inside altogether?
What do you mean?
Well, if I am testing an engine block, do I actually care what the internal nodes deep in the center of the metal are doing? If I just want to know how the whole object deforms on the outside, is there a mathematical way to only model the outside shell?
That brilliant conceptual leap is exactly what leads us into the final section of our text, the boundary element method, or BEM.
BEM.
BEM is introduced as a newer mathematical development, a direct challenger to the dominance of FEM in certain fields. And it does exactly what you just hypothesized. It essentially hollows out the object mathematically. It ignores the interior volume entirely.
Okay, I have been thinking about how to visualize this shift from FEM to BEM, and I think it comes down to chocolate bunnies.
Chocolate bunnies. Okay, proceed.
Traditional FEM, which we have been discussing this whole time, forces you to mathematically model every single molecule of solid chocolate inside the bunny. If you want to know how the bunny reacts when you push on its ears, you have to pack the entire volume, from the tips of the ears down to the tail, with 3D solid hex bricks. You are forcing the computer to calculate what the chocolate is doing deep inside the dead center of the bunny, even if the center doesn't really matter.
That is correct.
But the boundary element method sounds like a hollow chocolate bunny. You only have to map the thin outer shell, the surface of the chocolate, to figure out what's happening to the whole object. You completely ignore the massive interior volume. Am I understanding the math here?
I will absolutely validate the hollow chocolate bunny analogy. It is fundamentally accurate. That is exactly what the boundary element method accomplishes.
So how does it actually do that?
To understand how it does this, we have to touch on a very profound piece of calculus involving divergence theorems and Green's theorem.
More calculus? Great.
I know. But mathematically, what BEM does is it takes the complex governing differential equations that apply to the entire volume of the object, and through a series of complex mathematical transformations, it converts them into integral equations that contain only surface integrals.
Only surface integrals, meaning the equations are written so that the math only exists on the skin of the object.
Exactly. The mathematics prove that if you know the exact conditions on the absolute boundary of a continuum, you can infer the state of the interior without having to explicitly model it.
That's wild.
Because only surface integrals remain in the equations, you do not need 3D volumetric elements to fill the space. For a massive 3D solid object, you only need to wrap it in a thin layer of 2D surface elements like quadrilaterals or triangles.
You just wallpaper the outside.
Just wallpaper the outside. And if you are doing a 2D plane problem, you only need 1D line elements to trace the 2D outline.
That feels like magic. That is a massive, massive modeling advantage over FEM. By eliminating the volumetric domain meshing, by scooping out the dents inside of the chocolate bunny, you deeply reduce the mathematical load.
The reduction in computational cost is staggering. You have vastly fewer nodes, you have vastly fewer elements. Therefore, the global system matrix that the computer has to solve is a fraction of the size it would be in FEM.
And you don't have to worry about the messy inside.
Furthermore, you completely eliminate the headache of interior mesh generation. Meshing the complex 3D interior of an irregular casting is incredibly difficult and prone to discretization errors. BEM bypasses that entirely.
Does it have any other advantages?
BEM is also incredibly accurate for modeling problems that have infinite domains, like calculating how sound waves radiate from a speaker into infinite air, or how stress disperses from a tunnel dug deep into infinite soil.
Because it only needs the boundary.
FEM struggles with infinity because you have to put a boundary box somewhere. BEM handles it naturally. So if BEM is so much more efficient, if it saves all this computing power, solves infinite domains, and completely avoids the headache of internal mesh density, why isn't it completely replacing FEM right now? Why aren't we all just hollowing out our models?
The text provides a very grounded reality check on this exact question. While BEM offers incredible mathematical advantages, it is not a silver bullet.
Oh, there's always a catch.
First and foremost, FEM is far more firmly entrenched in today's computer-aided design or CAD environments.
It is the absolute titan of the industry. Every major software is built around it.
It is. FEM has been developed heavily and relentlessly since those first digital computer papers in the 1950s. Its element libraries are vast and highly refined. But more importantly, there is a physical limitation to BEM.
It's a limitation.
The boundary element method relies on fundamental mathematical solutions that assume the material is linear and homogeneous, meaning the material behaves the same way everywhere, like a perfect block of steel.
Okay, but real engineering is often nonlinear. Exactly. What happens if the steel gets so stressed it permanently deforms? What happens if you are modeling rubber that stretches to 5 times its length? What happens if you have an object made of 3 different materials bolted together?
The hollow bunny math breaks down if the chocolate is melting, or if the bunny is half chocolate and half peanut butter.
Exactly. FEM can handle highly complex nonlinear material properties, plastic yielding, large deformations, and multi-material assemblies much more easily and robustly than BEM currently can.
So FEM is just more versatile.
FEM can analyze a much wider variety of everyday, messy engineering applications. But as the text notes, the development of engineering applications for BEM is proceeding rapidly.
It's catching up.
It is still growing, still being refined, and we will absolutely see hybrid models in the future where engineers use FEM for the complex nonlinear interior and BEM for the infinite exterior domain, optimizing their workflows to an unprecedented degree.
It is absolutely incredible to think about the progression of this field. We have gone on quite a historical and mathematical journey today, and it is time to bring it all back home.
It's been a long road from closed-form solutions.
We started by staring at the wall of complexity, looking at how the messy, organic reality of the real world, the coffee splash, breaks our neat, closed-form equations.
Right.
We watched early engineers try to force that continuum reality into the rigid, rectangular constraints of the finite difference method, only to realize that the world is curved and jagged Minecraft edges create false failures.
Those artificial corners.
We witnessed the absolute breakthrough of Courant's simple triangle and how digital computers took the finite element method from a theoretical matrix nightmare to a practical superpower, assembling millions of mathematical Legos.
A true computational revolution.
We learned to deeply fear the constant strain triangle and the invisible stress spikes it hides, and saw how higher-order quadratic elements save us from catastrophic discretization errors.
The 8-node quad saves the day.
And finally, we looked at the elegant, highly efficient surface-level promise of the boundary element method hollowing out the geometry.
It really is a testament to the sheer willpower of mathematicians and engineers trying to predict catastrophic failure before it ever happens in reality. We have built an entirely invisible mathematical infrastructure to test the physical infrastructure we live in.
It's invisible, but it's everywhere.
But as we wrap up this deep dive, I want to leave you with a final thought to mull over. A bit of a philosophical extrapolation on where this numerical discretization ultimately leads.
Ooh, I love a philosophical ending. Let's hear it.
We've spent this entire time talking about how engineers break physical objects down, how we chop a continuous reality into tiny mathematical blocks or boundary meshes to approximate how things bend and break.
Yeah.
But consider this trajectory. As our computational power approaches infinity with the advent of quantum computing, and our finite element sizes shrink closer and closer to the atomic level, at what point does a numerical approximation stop being a simulation and start becoming an exact digital twin of reality itself?
Oh, wow. When our mathematical grids get small enough to account for every single molecule and its localized forces, the boundary between the mathematical model on the screen and the physical continuum in the real world might just disappear entirely.
That is a staggering thought. moving from a rough approximation of a coffee splash to a true one-to-one mathematical map of reality.
It's coming faster than we think.
Well, I want to sincerely thank you for joining us on this deep dive into the hidden math holding our physical world together. The next time you walk across a bridge or look out the curved window of an airplane fuselage, I hope you see the invisible triangles and matrices holding it all safely in place. Keep questioning the structures around you, and as always, stay curious.